Okay, next we go to series and parallel. If you look at here, we look at the Nmos transistor and PMOS transistor. But maybe you look at here first. If you have an Nmos transistor, to turn on this transistor, you need to supply a state 1 to turn on. So where to supply? Supply at the gate here and gate here. If they are in series, if this Nmos is in series, okay, what happened? This one will be turn on and on. Okay. If you want to have current flow, then you need to make sure both are turned on. So this is a condition when both turn on, then the output will be supplied to 0. And then you have another condition or other 3 conditions. If let's say one of the state is off, like this one off and this one off, then the output will not be flowing to 0. Okay, so mean to say both will be turned off. Are you okay? And then the last one is when you have both 0 and 0, then there's no way for this current to be flowing from A to B, then you will have an off condition. Meaning to say, if you want this to be working, both should be turned on. Okay, the end state. Okay, what about the PMOS? PMOS is that when you want this one to be turned on, you need to supply 0. You need to supply 0. So if both are supplied 0 and 0, then this one will be turned on and on. Okay, and the condition is this one will be turned on, because when this is on, then this one will be acting like a switch on. And then for the rest, if you have either one off or both are off, then the result will be off, and it will be supplied to high state or a 1. Okay. And then if this is in parallel, for the Nmos, you need to have either one is turned on, okay? Meaning to say you need to supply 1 at the gate. Either one should be turned on, or both should be turned on. So this one be turned on. Because if you have only one or both, you will turn on the condition there. And output will be going to 0. If you have a series for this OR condition, then you need to supply 0 to the gate to turn in order to turn on the PMOS. Okay, supply 0 to the gate, and then you will turn on this. So mean to say, if you have this and this, you will turn on the series a parallel circuit. Parallel circuit. Okay, so for series, both should be turned on. For parallel, either one should be turned on. Okay, for complement, a conduction complement. This is a complementary of CMOS gates that always produce 0 or 1. It's like our previous example, like inverter. It's either 0 or 1. So for any CMOS circuit, it should be complementary of PMOS and NMOS. So for this part, this is NMOS. And this part is a PMOS. Let's say our condition here for the two NAND gate. Why 2? 2 because we have an A and B input. A and B input supply to this NAND gate. Okay, NAND gate. Why NAND gate? Because we have this in AND condition, but we negate that from this PMOS. So we have a 2 NAND gate. All right, for series of this NMOS, this is a series, right? Series. You need, if you want to have a output on the Y equal to 0, you need to turn on both A and B here, or you need to turn on both the NMOS circuit. So for this part, Y will be pulled down to 0, or Y equal to 0. Okay, and thus, if you want to have Y equal to 1, then what should you do? Because PMOS here, they are in parallel. So either one should be turned on or both should be turned on. So you need to supply a 0 here and here, or either one should be a 0 to turn on the PMOS. Okay, so Y will be equal to 1. Why? Because this Y will be pull up to 1, the high state. Okay, so it requires parallel PMOS here. Okay, now done. So the rule of conduction complements is that the pull-up network is a complement of a pull-down. Yes, the PMOS here is a complement of this. Mean to say, if you have this in series, then the PMOS should be in parallel, just opposite of the condition of this NMOS. If you have NMOS in series, then you should have the PMOS in parallel. This is 2 input. This is also 2 input. Just opposite condition. So far, so good. So mean to say parallel should be, if parallel is the NMOS, then the PMOS should be in series. If you have the NMOS in series, then the PMOS should be in parallel. That's the complement part of these transistors.
Madam?
Yes.
Just now the diagram, I'm not sure which wires are connected, which wires are not connected. It doesn't have the dot to indicate which wires are actually connected, which ones are going over it.
This part, this is the green part, right? The drain part. So this is all connected to Y. Okay.
So everything else is not connected, is it? The one that's crossing, like A and B and all those wires.
No. This one, A, go to the gate of NMOS. This is a gate, right? Gate, and this is a source. This is drain. This is drain. And this is a gate, gate, and gate. Okay, so for B here, it is connected to the gate of NMOS 1 here. And this is NMOS 2. So the A here go to the gate of NMOS 2. But the A here should also go to gate of PMOS. PMOS. Maybe I should write down this is PMOS 2 and this is PMOS 1. Okay.
So and then A and the P1 is not connected, is it?
The A, yeah.
The P1.
A only go to only one of the PMOS here and NMOS here. Only one of them. So
the A, yeah, the B, can you connect that one? Okay. All right, that will be the complete diagram.
Okay, so this one source and source. So source should be connected together like this.
Thank you, ma'am.
All right, you're welcome. Okay, we go to the next stage. Let's say you have a compound gate like this. This is this equation, right? And you know that if you have, what is this one? The dot there. A dot B, and then you have a C dot D. Is it AND gates or OR gates? What do you think? If you go back to our previous example here, this is a, this is a NAND, right? This is N, yeah.
Yeah.
And it starts from down here, right? This is a N connected in series. So if we refer to our example here, this is N, this is also N. So A and B should be connected in series, and C and D should be also connected in series. So I mean to say you have to have like this, C and D in series. What is this? They are Nmos, right? Nmos first. Always start with Nmos and then you build up using the PMOS. Okay, so you need to consider this one, the A and B. Why A and B? Because the equation here give you A dot B. So you should have A and B in series with this Nmos transistors. And while C and D should be in series, and there should be 4 Nmos. And then you go to the next step. The next step is look at the middle here. This is plus sign. So what is plus sign? An OR gate or AND gate?
OR gate.
Plus sign is OR gate.
OR gate.
Yeah, good, very good. So what should you do? This side and this side should be combined with a OR gate. And you know that OR should be in parallel, right? Parallel. So how to combine? You just connect the drain side and the source side. Okay. So when you connect this, you have 2 in parallel because they are connected here and connected to here. Okay, so this is the drawing. So far so good. And you need to know that
Yes,
down here should be the ground because this is a source. And here should be to the output because this is the drain side. But to simplify, we will not draw you this. This one, hold on. And then you go to the next step because this is already done for Nmos. All this for Nmos. And then the negate part, negate. Negate is actually for the PMOS. So what should you do? You just inverse everything or do the opposite thing for our PMOS. So since we have A and B in series, you should draw the A and B in parallel. So A and B in parallel. But what is that parallel? The PMOS. Okay, PMOS. So make sure PMOS with bubble. You have a bubble here. And this is A and B. So you write down the first gate is for A and the second gate for B. And then same to this side, you have a C and D. Since they are in series, you should do opposite thing for PMOS. So they are in parallel. Okay. And then now you have this. The next step is for this part, you do the connection of parallel, right? So in our PMOS, this is parallel. And for our PMOS, you should connect in series. So where is that series? You need to combine the first one, the first one, the first one here and the second one here in series. So that's why you have AB connected here and CD connected here in series. Where is that series? Remember, series is when you have one element to another element, they should connected to side by side, right? So you have 1 and 2. So that's where is that series there. So where is that source and drain? Source should be here and drain should be down here because it's opposite from our Nmos. Okay. All right. So what is the Y output? Y output is the combination of this part and this part. So if you have, this is a PMOS and this is an Nmos, you just combine. So you have the first one here. I just remove this. You have this Nmos, and this is PMOS. So the Nmos should be down here, and the PMOS should be up here. Okay, and like I said, this is the drain. This is source. This is the drain. This is a source. This is a drain for Nmos. This is for PMOS. So PMOS here, you have as the source here, and the drain should be connected all to output. And the source should be, source for Nmos should be connected to ground. Okay, so source for PMOS should be connected to the higher polarity or the VDD. Usually we don't put VDD, just put it like this way, like this. Okay. And what is the symbol for this? Since our output, if you look at AB here, this is N, okay, and this is also N. So you have over here N and N, okay, with two input. This is A and B, two input, and C and D with two input. So you have two input here and two input here. All right. And what connected to these two ends is this one, the OR. So OR should be here, the next stage. What is this one? Okay, this is a first stage. First. Okay.
It's okay, Dr. Arfan. I already let him in.
Oh, sorry. This is a first stage, and this is a second stage. Second stage. So this is our second stage here, the plus sign up here. And then the negate sign here is this part, the bubble, right? So this is our symbol, the gate symbol. Is it clear? Do you
Yes,
have any?
Doctor, for now, until now, it's still clear.
Okay, alhamdulillah. All right, very good.
So, ma'am?
Yes?
You need to have the PMOS side of things because we have the bar in the equation, is it?
The bar is actually the negate side or the PMOS. This
so
part.
to negate
the complementary, so that means you have to have a set of N for pull down and a set of P for pull up.
That's why in your previous slide here, they put it a complement conduction, right? A complement. Why complement? First you have the Nmos, and then second part you should have the PMOS. But for PMOS you need to do the negate side or the opposite side of the Nmos. So that's why you have both. One is for Nmos, and the other one is for PMOS here. So this side just for PMOS. Down here is the Nmos.
So adding that PMOS side will come to negate the whole equation.
Yes.
Underneath. Okay.
Yeah.
Okay, understand.
Okay, good. So this is a negate part. This one just for symbol. Okay. So what is inside this? The gates here is this. The pass transistors or all the transistors inside this. So how many transistors we have? If you look at here. How many transistors?
8.
Yes, 8. How do you know? You just count, right? This one, 1, 2, 3, 4, 5, 6, 7, 8. So we have 8 for this combination. We call this as a compound gate. We have 8 transistors. Right. Let's go to our next example. Okay, over here they put it as how many input. From here, how many input do you see?
4.
4. What are they?
A, B, C, D.
Yeah, very good. Okay. And then if you look at the plus sign on the left side, this is for OR, right? So we call it as a, since we have 3 input, 1, 2, 3, we call the operation here as a OR, yes, OR, that's why you have O there. And then you have dot sign here, dot sign is the N, but since, yeah, we have only 1 input there, so we can call it the OR3, and what is I? I is the invert side, invert. So that's how they come up with O3 AI. Okay, but now we are not going to concentrate on that, but we want to draw the transistors of this Y output. So how to draw this? Where to start? What do
Start
you
with
think?
inside the bracket first.
Okay, inside the bracket. Okay, but Nmos or PMOS is it? What is this transistor?
Nmos
Start
first.
with Nmos.
Always start with Nmos.
Nmos.
So since you have OR here, so what should you do? OR is in
Or
parallel or in series?
parallel.
It's parallel. So what you do? You just draw the
3 Nmos in parallel.
yeah Nmos in parallel. So make sure you have 3. Okay, like this. Then this is number A, B. This one just follow exactly what they have here. So you have all 3 here. Then next, you have N. This is N. So where to connect this N? N should be in series or parallel?
N is series.
Series. So the whole thing here should be connected to this D
Series.
in series. Okay,
Yes.
so you should have 1 here. And this one should be to D. And like I said, down here should be what? A source, right? Is it a source?
Yep, that's the source.
So source should be connected to ground. Okay. And then the drain should be connected to, this is drain, to Y. And then the negate side, invert. So what should you do? How to invert that? Since these are in parallel, so PMOS should be in series, right? So how to draw that? If you have a series, maybe I should make it smaller, right? Or just move it here and erase everything. Okay, so the negate side, this is the Nmos here in parallel. So you should have that one in series. So this one, the PMOS should be in series. Okay, you have that 3. And then what else you have? This is A, B, and C. It's okay. Anywhere you can put A, B, C. The other way also can. And then since both here are in series, so what is the opposite for series?
Parallel.
Yes, parallel. So you need to connect to parallel side. Where is it? It's over here. So even though my drawing is not that cute, you can just maybe readjust here and there. Put it over here so can, no problem. So you have a D here. And here you should have a VDD connected to the source. Okay, this is drain. Is it okay? Is it clear? Or do you have question?
Clear.
Clear, right? So this is series because we negate that side, the parallel side, And then since this is series, you have to connect all here in parallel. That's why you have a parallel side. Okay, Alhamdulillah. So this is your yeah, the transistors. Now the group discussion. I think that's why you need to go to your groups. You have your groups, right?
Okay, so wait. Before we go to the group, I want to have some housekeeping here. Okay, so what we are going to do is I'm going to enable you guys to use a Jamboard so that you can discuss among your group. This is not the exact group that you have requested because some of you guys are not here. So I put in some of them are random. So here, okay, you're going to please take note of this equation. Can you guys write it down? Because in your group, you are going to be doing this transistor, you are going to sketch this transistor, the transistors that will form this equation. Is that clear what you have to do? And after this, I will share the Jamboard location. Okay, baru nak masuk lah surah ni. Okay. Okay, so I will share the location. Okay, now I lost my train of thought. Okay, so here I will give you the location now. Anybody doesn't know how to use Jamboard? Okay, I'm going to put it in the chat box. 1 second. Okay, so if you go to that Jamboard, you will have, you will be able to draw in the Jamboard. Okay, do you need me to share or you guys, I will check later whether you guys are able to access the Jamboard or not. So, but if you just click and you create one page according to the number of your room. Okay, so for example, room 1 will be page 1, room 2 will be page 2, room 3 will be page 3, and room 4 will be page 4. Okay, everybody got the equation? Yes? Now, if everybody is all set, I'm going to send to your rooms. Yeah? Everybody okay? Okay, here we go. Bismillah.
This is advantage you to join breakout group.
Break.
So Provanis, I got invitation to room 5.
Yeah, you are, I mean, you and me are in one room. Lah.
Oh, okay, okay.
Okay, so let's see, group 1. Dr. Arfa, you want to take over?
Yeah,
Is this correct?
this is correct. A, B of the Nmos should be in or position or parallel. And then CD for the Nmos should be in series. Yes, because there are N. And then both should be combined with parallel, in parallel. So just invert for PMOS side, yes, but there's something missing. For PMOS, you need to, yes, you draw the bubble, but you miss this side. Can I draw something?
Yeah, but you have to open your own.
Oh, okay. Or maybe I just share something. Share the screen. Okay. You need to have this. This is a PMOS. Okay. This side. I think you missed this part. Can you see this PMOS?
Just one line.
One line. You missed one line. Okay. I will unshare my screen. Cuma nak unshare. Stop sharing. Okay. Okay. Then,
Good job, group 1.
okay, group 1, good.
Okay, group 2.
Group 2.
Okay.
Group 2, CD, okay, AB, yes. In parallel both, yes. This one, the source side. The source side for PMOS. That A transistor there. This one, the source side is connected to ground. This is a symbol for ground. So you should put a VDD symbol. Yeah, like that.
This is the VDD symbol.
Yeah,
But I noticed a lot of you guys use this for some reason. I think because in microwave it looks like that. But actually the official, this is the VDD, okay?
The actual.
I cannot write using my mouse.
All right. The
Okay.
rest I think, okay.
But otherwise, good job, guys. Group 2.
Mm.
By the way, Kai, who is this Kai? Can you give me your full name? If not, I don't mark your attendance, eh?
I'm Khairi Irfan.
Oh, Irfan. Okay.
All right. Okay, group 3. Group 3, yeah, sisters. So this one connect to VDD or ground?
Oh,
Hello?
wait. That should be the VDD.
VDD.
Okay, this is VDD and this N connect to?
It will be connected to ground. I mean, it should be connected to this one.
The one at the
on
at
the
the
right.
right. On the
Yeah.
right.
Y didn't finish. Okay, this is Y,
Yes.
right?
The output.
Yes.
And this is ground.
Ground will be down there.
Okay. All right. Now next group, group 4. Okay, so this one is VDD and yeah.
I think the C and D transistor, not enough bubble and stick.
This is complete the transistor.
The CD on the PMOS side.
This one, there's no bubble here.
Mm-mm.
Okay.
Mm-mm.
Actually, they wanted to draw this. You guys got this?
Even I think even the drawing inside the picture, I think there's no bubble for
right?
PMOS.
So you have to add bubble here.
You need to be careful because they're PMOS. And that source should be connected to VDD. Okay, good.
Okay. So now we continue back to the slides. Okay.
Ma'am,
Yeah.
just now in the Jamboard answer, the CD on the top side, CD and AB was inverted. So that doesn't matter, is it?
Oh, you mean this one, whether it's here or you put it up?
Yeah, whether one is down or top, it wouldn't matter in the
it doesn't matter.
Okay.
Later when the drawing, you go to the layout, it might matter, but that one is for functionality right now, it doesn't matter.
Okay.
As long for PMOS, it should be PMOS, and NMOS should be NMOS. Okay. All right, I will share my screen.
Yes.
Okay, very good job, everyone. Right, now we have the NMOS and PMOS transistors. This is a single PMOS and NMOS, or we call it as a pass transistors. So this is N, this is P. How do we recognize that? Just look at the bubble or no bubble, right? If you want to make this one as a switch, what should you do? You need to control the gate. Control this gate and control this gate. So if you turn on of this gate, the drain side will take the input side or the source side. So meaning to say, if you switch on the gate or you supply one, then you will have a switch turn on like this. Okay, turn on. Then the output will follow the source, or we say that the current will be moving from source to drain. And then, yeah, we will have something. But if we turn off the gate, turn off, then you will have that switch off or open the switch. And then the output will be equal to 0 or follow the source side. Okay, but since this is an Nmos, and you know that Nmos always connect to the ground, right? The ground side. The source always connect to the ground. So meaning to say, the output here, which is the drain, will pull down to 0. Pull down to 0 if this is turned on. Okay. What does it mean? The drain will be equal to 0. Yes. And the Nmos will pass a strong 0 because for Nmos, it always pass a 0, a strong 0. If it pass a 1, it will be a degraded 1, not exactly 1. Or if you have a VDD value of maybe, let's say 5, it will not exactly give you a 5 if you use the Nmos as your pass transistor to pass VDD. So mean to say, if you want to pass a 0 or the ground, then you should use the Nmos. Do not use Nmos to pass a VDD. It will be a degraded VDD or a degraded 1. Okay, for PMOS, we also control it by the gate. And you know that we have bubble here. Since we have bubble here, in order to turn on the PMOS, you need to supply a 0. So supply a 0, then you will turn on the switch. Okay, on switch. And then the drain will follow the source. And we will have a, if the source is 0, then we will have the drain equal to 0. But it is a degraded 0. Why? Because like we mentioned in previous case, a PMOS always have a, this is drain side, this is source side. So source side always connected to higher in polarity or the VDD. And this is output. Since this one turn on, then the output will pull up to VDD. So meaning to say it will give a strong 1 or a strong VDD. A strong 1 means if VDD is equal to 5, then it will pass exactly like 5. And this is not good if you have a 0 output. It will give you or pass you a degraded 0. Okay. So for PMOS, if you want to pass a VDD, it's better to use PMOS. If you want to pass a 0, then it's better to use Nmos. All right. Okay, this is for 1, this is for 0. So far, so good. Okay, we go to signal strength. This is basically what they mean of that previous slide. So the strength of the signal is actually how close it approximates to the ideal voltage source. Meaning to say, if the voltage source equal to 0, then you should exactly have that 0. Or if you have a voltage source equal to 10 volt, then ideally you should get 10 volt, right? And then you have if you have a VDD, then we say that it is a strong 1. If ground, then 0. Remember, we have 2 types of source, either VDD or the ground. And then for Nmos, yes, it should pass a strong 0 if you connect it to the source. Yeah, and you want it to pass 0, so it should give a strong 0. But if you pass a 1, then it will be a weak one or degraded one. And for PMOS, it should pass a 1. And if you pass a 1, then you will have a strong one. If opposite, then you will get a degraded 0. So for Nmos, it is best to have a pull down network. And for PMOS, it should be a pull up network. Okay, PMOS, that upper side, and this is upper side, and this is the bottom side. Transmission gates. Prof. Anis, do we record this one?
Yes, it's recording, right?
I think we pause it a little bit before.
But here it's written recording. It's recording.
Okay. So transmission gates. Okay, what is transmission gate? Okay, just now we have a pass transistors that produce degraded outputs. We have 0 or 1. Either it's a strong output or a strong or degraded output. So a transmission gate should pass both 0 and 1 very well. If we have that Nmos and PMOS combined together and we put it in parallel, or we put it like this one, and we have the source and drain, or the A and B here, and we have the G is the gate, and the GB is a G bar. G bar means negate of that G. So if you pass a 0 or you supply G as a 0, then of course negate G bar should be 1 at here, 1. And then since this is a what we call it, Nmos up here, this one will be turned off, right? Nmos. In order to turn on Nmos, you should pass a 1. So if you have this, then the output should be equal to, if you pass A here is a 0, then if this one 1, turn on this one, switch is on, then the B will take the A. So since this is a 0, then B will be having a strong 0. Because why? Because you have combination of both Nmos and PMOS. And then if you turn on the gate here, but E here now becomes 1, then you will have an output equal to 1, or also a strong 1. So meaning to say a transmission gates always give a 0 and 1, a strong 0, and also a strong 1. Okay, so regardless of what you have both PMOS and Nmos, then you will have both a strong 0 and 1. And then the rest here, this is other way to draw the transmission gates. But all three here are difficult to draw compared to this part. So sometimes they just use, they just draw like without the G bar. But we know that that side actually negates. Okay. Right, 3 state. A 3 states is when you have, usually this one just for 3 state buffer. This is a buffer, okay, buffer. A 3 state buffer produce Z when not enabled. Meaning to say, maybe I shall put it this way. If you have a 3 state, meaning to say you have 1, 2, 3 input and output. Okay, 1, 2, 3. It is controlled by this enable side, okay? And then what should you look for? First, you look at the input, what input it supply, like maybe this one, 0, 1, 0, 1. Okay, and then you look at the enable. If you have, let's say I put it, this one as a 1, and then enable is 1 to turn on. So this is 1, and this is 1. Then the output will be equal to 1. Okay. But if you have, this is 1, the input is 1, but now enable is equal to 0, this side. Okay, remember there's one state that we have in the previous slide, the first slide, I think, yeah, this one, the floating side, the Z floating side. When pull down is off and pull up is off, then you have a floating Z there for output of Y here. Okay, so means to say if you have even though the input is 1, but enable is 0, then the buffer side here will have an output equal to Z. Okay, and what about if you have another side, which is negate of that side? Remember this is 0, and enable is 1. Then you should have a Y equal to that enable, or like this. This is a 0, then enable is 1. So you should have an output equal to this one. Sorry. For another way, if you have this is a 0, maybe you should focus just on this side. It will take the A and B if this is on, if this is turned on. It's easier to look at this side down here. If this is an input, okay, and look at the enable. If the enable is 1, then it will pass the A. So Y is equal to this. Follow the A. But for enable is 0 for both cases, then you will have the output equal to Z if this is 0. So mean to say it is controlled by enable.
So the Z, it could be any value, is it? Undetermined? Or is it a fixed value? Oh, okay.
A floating value. So you look at the enable, make sure this one is turned on. If this is turned on, then it will follow the A. Y is equal to A, just that. If enable is 0, then the output will be equal to floating value of Z. Right? Okay. So far so good. I hope I don't confuse you guys. Just look at this side down here. Okay, now non-restoring 3-state. Okay, the transmission gate acts as a 3-state buffer, and it only has 2 transistors, 1 and 2. But for transmission gate, it is a non-restoring gate. It will not store that. So noise on A here will be passed to Y. This is after several stages. So the noise may degrade the signal beyond recognition. So meaning to say, because of it is a non-restoring, it will pass whatever we have at the input. Okay. So if let's say we have only 1 transmission gate, this is still okay. But what if you have so many transmission gates? This will degrade your system performance. So it is not good. Then we have another case. We call it as a 3-state inverter. We invert that 3-state. So 3-state inverter produce a restored output. Okay, so However, that the three-state buffer, it ignores the conduction complement rule because we want an output of Z. Meaning to say here, if you look at the this is a three-state using pulse transistors. Coming from where? Coming from this. So how many states? We have A here, and then the enable. You have enable 1 and also the negate of enable. And then you have the Y. So you have three states. And then if you look at some condition, which is the condition of when you have both at NMOS and PMOS, 0, or 0 means open circuit. If this is open circuit and open, then you will have
The enable is off. Yeah.
Yeah. Oh, yeah. Sorry. We have also a condition of that enable is off. That's why this is open. When enable is off, means it supplies at this gate of 0. Then this one will be turned off. And then enable bar of this side will have a supply of 1. Then this PMOS will be turned off or open circuit here. So since both sides, the P and the NMOS is open, and you know that a series circuit should have a shorted path, right? In order for both to work. So since both are open, then Y will not go anywhere. Mean to say Y will be floating. Or floating, we put it as a Z, the Z. So far so good.
Yeah.
What do we need when do we need, in what conditions would we require a Z output?
Z output.
So when do you think? Any idea?
Floating, when it's floating, it's ready to be in any state, right?
Yeah. So you want when it is on, it is conducting. You see enable is on. So this path is on. The Y path is on. So either when you put in either A equals to 1, then it will be pulled down, or A equals to 0, then it will be pulled up. So at any point, there will be power consumption, right? Okay, but the reverse, when it is Z, will there be power?
No, there will not be any power.
Yeah, so actually you introduce the Z state in order to reduce power. So you want the signal, you want the circuit to be there, but you don't want it to consume power.
I see, okay.
And okay, so just the tri-state means you have 0, 1, and Z. These are your possible outputs.
Okay.
All right, Dr. Alpha, you can continue.
All right. And then we have another condition when enable is equal to 1 here. So if this is 1, then NMOS should be turned on. So that's why you look at here, you have a turn on side. And then when we negate the enable, so you have a 0. If you supply the gate of PMOS 0, then this one will be turned on. That's why you have a switch on for both sides. And then here, the Y here, it will follow the A negate. The A negate. Why negate? Because you have the A result here, but it will negate this. Since this is a tri-state inverter. Okay, the tri 1, 2, 3 inverter. Inverter is this part. Okay. Now, multiplexer. Okay, by the way, the most right side here is the symbol for tri-state inverter. Okay, for multiplexer, okay, you have this symbol. And then a multiplexer on your right side here is actually a 2 input with 1 output. So you have 2 and 1.
Alpha, maybe we have to speed up a bit because we have like 10 minutes more.
Oh, okay, sorry. Okay, last. Okay, a multiplexer will always choose between two input. So you have this input, right? The D0 and D1. Okay, the Y here will choose either this or this. It is actually according to your the S condition. So like this one, it will choose the Y here. It will choose this. So this one will have a 0 and 1. And this part, it will choose, with the Y here, it will choose 0, 1 here. So the output Y will be equal to, since it choose this side, so you have a D0, and then with S, the S, D0 with S bar, because it will choose this side. And then for this part, it will choose a D1 with S. Okay, so this is what they have. Okay, and this is what the equation. And if you put it in terms of transistors, both are equal, but the way they put it is quite different. But if you look at on this side, how many transistors you have? If you count, then 2 plus 4 plus 4 plus 2, 2, and plus 4 and 2, you will have 20 transistors just for these gates. So you don't want too many transistors. You want to reduce that. So transmission gate, yeah, it is a non-restoring mask, uses two transmission gates. So you have this part, and this is how they configure in terms of transmission gates. We have only 4 transistors. Coming from where? From 1, 2, 3, and 4. So this is your group discussion.
I think we can skip the group discussion because we don't have time. So can you go back to slide 40?
40.
Yeah.
Okay, here.
So, so if you can see here, if the S is high, so this S is high, the down part here. So the Nmos at the bottom part is on. So, and S bar will be 0. So the bottom half of the transmission gate will work. So Y will be equal to D1. And when S is S equals to 0, so S equals to 0, the top part will be on. The top part of the transistor will be on, and S bar will be 1. So the top part will be on, so Y will be equals to D0. So in this way, this transmission gate marks can implement the equation using 4 transistors only. Unlike the CMOS or the complementary configuration, you use 20 transistors, right? Can we go back to slide 38 for a while? Here. So this is known as static CMOS or complementary CMOS, where you use each gate, you have the PMOS and the NMOS. And you have the way that you connect them, the one that we showed earlier. So this one uses 20 transistors, and the transmission gate uses much less transistors. Okay, Dr. Arfa, you can continue with the next slide 42, I think.
All right. So, okay, inverting mux, they use inverting multiplexer, inverting, and this is a compound gates where we already discussed in our previous example. And if you want to put it in a tri-state inverter, we can configure it this way. Tri-state in series of each other. This is tri-state number 1, and this is tri-state number 2. So essentially they are the same, yeah, both are same. And then this is a symbol for multiplexer, inverter. So non-inverting multiplexer adds an inverter. So if you want to have, this is just for 2 inputs, right? 2 inputs. Yeah, both also using 2 inputs, the D0 and D1 here, D0 and D1 here. But let's say you have a 4 inputs, what should you do? You can also have a a combination of a multiplexer, the two input here, but we combine in terms of 1, 2, 3 here. Yeah, we have one stage here and second stage here. And then the other way is to have it in series of 4 tri-states. So you have 1, and then number 2, and then number 3, and then number 4. So you have 4 inputs, 1, 2, 3, 4, and also you have 4 input at here. So both are same, but the way you draw it different. Okay?
Okay. So I think we finished, right?
Yeah, finished.
Okay. So just to remind you, on Thursday, actually it's supposed to be an official holiday, but we will have a short quiz. So we will put in the quiz in the Google Classroom. You can log in and do the quiz. The quiz will be using quizzes, and we will cover all the material that has been covered in these past few classes. All right, so Dr. Arfa will share the slides and the video later in the Google Classroom, so you can check that. So the quiz is going to be just half an hour. So I will enable the link in the Google Classroom, and you can just answer. Okay, and we will not be having class. Maybe later I will put in a video. But otherwise, the quiz is just the thing that you need to do. Okay, any questions?
Madam, including today's topic as well for the quiz?
Yeah, including this topic as well. Any other questions?
Madam, for the lab, do we have to do the transistor sizing?
Again, I couldn't hear Aina.
For the lab, do we need to do the transistor sizing? Because I see that Brother Muhammad didn't include in the marking rubric.
No, you can use the transistor size for the inverter. Of course, there is a transistor size, right?
The L and the W, yes.
Yes,
Okay.
for the inverter.
So don't need to do the calculation for that.
Oh, no, there's no no, not for this first lab. Later we will have it when we have.
Okay. All right.
In the rubric, it's just the timing, right?
Yes, only the timing and the yeah, timing only.
Yeah, so this one is just the introductory lab. I just want you to be familiar with the microwave first. Make sure you have all your timing diagram correct, and get used to the tool. And then later we will start to put in more complex. Okay. So you just drop in your assignment into the folder at the Google Classroom. Okay, any other questions? Everybody's okay? So we will have the quiz 8:30. If you have you finish early, then you can have, it should be half an hour like that. Okay, no other questions. I think we can end.
Thank you, Prof. Anis. We end with Tasbih Kafara and Surat Al-As. Subhanakallahumma wa bihamdika asyhadu an la ilaha illa anta astaghfiruka wa atubu